In this chapter we're looking at differential equations, and a differential equation is simply an equation that involves at least one derivative. So here you can see that we've got dx dt, we've got dy dx, and here this is d squared x dt squared, which would be the same as if you wanted to write it, it'd be like x double dash minus 4x equals t. Okay, so that's a second derivative. The other thing that we've got here is the notation. So if you've got a function where we usually write it as y as a function of x equals something, we're now going to be looking at y where x is a particular value, so say when x is 0, and that might be 4. So what that corresponds to is the point 0, 4. When x is 0, y is 4. Now, differential equations are so important. They're used in all different aspects of science and engineering, biology, chemistry. They turn up everywhere, and they help us understand rates of change of things. So, for example, in the body, rates of absorption of certain drugs, say if we were looking at medicine, or they might help us in engineering to understand the deflection of a beam or a building in wind. So they're very important to a range of applications. So the first thing we're going to look at here is how to verify a solution. Now the word verify means essentially to prove that a given solution, y equals, and here we've got the solution, is actually a solution of the differential equation. We tend to talk about differential equations as DEs, by the way, so often I'll just talk about a DE, which means differential equation. And hence find the particular solution of the differential equation given y of 0 equals 3. Now, we'd be given a condition like this because we're going to need to find c, and that's our constant of integration. So that's the reason we'd be given a condition. Because this is a first order differential equation, order means how many times you've differentiated it. So this is first order because you're just looking at a first derivative. First order differential equations, when we integrate them, are going to introduce a single constant, and that's why we've been just given the one condition. If we had a second order differential equation, we'll get two constants when we integrate that, and so we'd need two conditions. But for now, let's start off with verification. So we need to show that dy dx equals x plus y, where this is y. So first thing I'd do is write down what y is. A is a constant, and I know that I'm going to need dy dx, so I'm just going to differentiate this. E to the x stays the same, and x turns into 1. So now we're going to show that this is equal to this. So dy dx equals x plus y. So x plus y equals x plus, and this is all y, so a e to the x minus 1, which equals, now the x's cancel, and we have a e to the x minus 1, and you can see that that equals dy dx. So therefore, comparing the dy dx that we found and the x plus y, we can now show that dy dx equals x plus y as required. So the key here is to show what dy dx equals by differentiating your solution y. For part B, what we need to do is find a particular solution of the differential equation. Now this is y here, and we actually need to find what a is, basically. So we know that y of 0 equals 3, so that implies that a e to the 0, so x is 0 everywhere, equals 3. E to the 0 is 1. A take away 1 is 3, so a equals 4. So therefore, our particular solution would be y equals a, and a is 4, 4e to the x minus 1. Now the difference between a particular solution and a general solution will have a constant in it. So this particular solution here is general because it works for any a. Any a actually satisfied the differential equation. For a particular point that we're given, so 0, 3, that's where we have a particular solution. So this is only a solution where we are satisfying that point 0, 3. That's a unique solution for this particular point. So that's the difference between a general solution for a differential equation and a particular solution for a differential equation. So the key with these is going to be integration, trying to find our solution y by integrating a dy dx, which we'll do in the next few examples.